So there do exist people, but show T is a, hey, yay, good call. Is it you, Emma? Yeah, you got it. And see, I like this one because I can see whether or not you know what it means to be a linear transformation, and I don't have to, sift through lines and lines and lines of garbage, right? I mean, if you have a clear mind of, what's a way you could make this worse would be to like write A and B out in terms of components, but I don't think anyone did that. But my point is here. Okay, so it shows the linear transformation. Suppose M is invertible. Prove T is a surjection. Aha. So how do you prove something's a surjection in a context like this? If you want to be super tricky, you could try to use dimension theory, right? But more often than not, when I ask to say prove something, when I ask to prove something's a surjection, there are two different possibilities. The one is that I'm trying to push you towards using the dimension theory to prove that the dimension of the range has to be equal to the dimension of the codomain. If you could prove that, that would prove that it's onto, right? Supposing that the mapping is well defined. But the other thing, and more often, this is also very often the case, is that I just want you to show me through direct argument that it's a surjection. So how do you show through direct argument something's a surjection? You pick a specific but arbitrary element in the codomain, in this case Rn by n, so B. And then you pick something in the domain, in this case M inverse B. And you show that the image of that element is your arbitrary thing in the codomain. That proves onto, right? I didn't show you my scratch work. I'm not saying you can't put scratch work on your test. Just make sure that your proof is clear, right? Make sure that at the end of the day, you've written something that has the clear structure. I've picked an arbitrary element in the codomain. Here's an element of the domain that maps to it. Therefore, it's surjective, right? If you take these sentences and write them backwards, I won't give you a lot of credit. That's what I'm trying to say. Even though we all know that's how you find it, Linear independence is the other thing you guys didn't say much about in the 3 minutes I gave you to forecast the test. But linear independence is a big thing. Here I've asked you to prove what? So I got a linearly independent subset. X not in the span. Prove that X union that X is linearly independent set. Now, maybe to be more clear, I should have said, do not use, dimension theory. I probably should say that to try to make sure you guys don't go the wrong path. Like I really am looking for, in this question, an argument along this style, like direct confrontation of the definition of linear independence spanning, how that all works together. Let's talk about the proof actually for a second. So if X is not in the span, that means that suppose that it was. Suppose that, let's see here, that's linearly independent, and suppose X is not in the span. I want to look at this and prove it's linearly independent, right? Which means I need to show that these coefficients are all 0. So I said, suppose one of them is non-zero towards a contradiction. And I started out by supposing that k plus 1 is the non-zero one, right? If k plus 1 is the non-zero one, then that would give me x is equal to that is in the span, which is clearly a contradiction, right? Therefore, we can rightly assume that ck plus 1 is equal to 0. But that then leaves me that this is equal to 0, which by the assumed linear independence of S gives me that all those coefficients are 0. Consequently, all of the k plus 1 coefficients are 0, which gives me linear independence of S adjoin X. That's actually the plus in the plus minus theorem that I mentioned, right? So. How should you study for that? Should you try to memorize the proof of those theorems? No, I don't think so. I really don't. I think what you should make sure you have clear in your mind, what is the definition of a span? How do we test for linear independence? And just have confidence that you've prepared yourself enough that you have a shot at it. If you try to memorize the proofs of things like that, it's too much. And you'll just half remember it. And when you half remember it, I can see you're memorizing, and then I will typically take off points. because I'm not interested in regurgitation. I'm interested in like you understanding concepts, you know? So I don't want to reward memorization is what I'm trying to say, right? But of course, you do need to, you need to know the definitions. But memorizing the definitions isn't really what you're trying to do either, is it? You want to understand the definitions. You need to have, this is an example of this. This is a counterexample of this. Think about what theorems allow me to manipulate this idea. These are things we should be thinking about. What is that? I can't read. 27, all right. Oh, look. As I suspected, there's one of these, right? Ooh, look at this one. Let F be a field with 2 not equal to 0. In other words, it's a field not F characteristic 2, which is the evil field. Symmetric matrices, A sub n, antisymmetric matrices. We've got to map psi from the Cartesian product of Sn and An to Fn by n. And how do I define it? A plus B. Prove that it's an isomorphism. Show details, yes. Interesting. Let's see here. So I show, first of all, that it's a linear transformation. Then I show that the kernel is just 0, so it's injective. And then what's last? Still need to show it's onto. But, hey, this just hasn't come up this semester for us yet, guys. You guys remember from calculus where we show you that any function can be written as a sum of an even and an odd function if the domain is symmetric about the origin? You guys seen this ever? So for example, when you apply this to e to the x, you get can you recognize? Cosh x, sinh x. So this general identity motivates why we talk about cosh and sinh. Cosh is the even part of the exponential. Sinh is the odd part of the exponential. But this algebra trick up here, to me, it feels the same as the corresponding algebra trick for matrices. A is 1/2 A plus A transpose plus 1/2 A minus A transpose. Now, I have not written this in class until now. Wait, we're still not in class, so I probably will never write it in class. But we had a homework problem which kind of touches on this, didn't it? We had that T of A is equal to A plus A transpose. You studied the invariant subspaces. You saw that it basically multiplied the antisymmetric ones by 2 and it just killed the symmetric ones. That's in the same circle of ideas as this problem. But so this is just an identity. What's this identity show? This is symmetric. This is antisymmetric. You can check it out, right? If you take the transpose of the symmetric piece, you get back the same piece. If you take the transpose of the antisymmetric piece, you get minus that. And that's actually what you need to see directly that it's a surjection, this map. See, because if you look at this and that as inputs, you get back A for any A. So that shows that given any A in Fn by n, we can map to it by this pair. And by the way, that's symmetric and that's antisymmetric and it maps to A. So this is a surjection. In summary, psi is an isomorphism. Yeah?
If you didn't see that, is there another way to show it, or that's the only way?
How would you see it otherwise is a good question. Here's another way. You could calculate the dimension of the symmetric matrices. You could calculate the dimension of the antisymmetric matrices. You could show that the sum of those dimensions is equal to n squared. And since we know that the dimension of V cross, if we have a vector space V cross W, the dimension of V cross W is dimension of V plus dimension of W. So since the domain is Sn cross An, the dimension of the domain is, you know, well, but that still doesn't show. No, it would show that, because if you could show that the dimension of the domain was equal to the dimension of the codomain, then we have this theorem which says that a linear map from a n-dimensional vector space to an n-dimensional vector space, in this case n-squared dimensional vector space to an n-squared dimensional vector space, it's one-to-one if and only if it's onto, if and only if it's a bijection, linear bijection. Remember that we have the following are equivalent theorem, but that is built on the basis that we know the dimension of the domain and codomain are the same. Before the fact, it's not known to you that the dimension of Sn cross An is the same as the dimension of n squared. But if you could prove that it was the same, proving it that it's one-to-one automatically proves it's onto, and frees you of not knowing this algebra trick, yeah. Of course, now you know the algebra trick, so you will not pursue the direction I just did if this came up. But yeah, this is a hard problem. Right. Yep.
What did the very first part of the directions on that, where it was like the field and 2 0, where did that come in?
3. I read a half. I can't write a half when 2 is equal to 0. Oh, look at this. Here I have basis beta, basis gamma, linear transformations from T to W, linear transformations from W to V, find a basis for that in the matrix, and then find an isomorphism from this to this. Yeah. So I'll leave that there. I think it's been up on the screen long enough that you've seen it, right? Okay. Yeah, that was it. One person solved that last problem. So maybe 2. No, just 1. So that was the test last year. Yeah. If you think about it, you've got a pretty good chance at it if you just have the subspace test theorems really down pat and the coordinates really down pat. If you ace that material, you already have a C, more or less, right? But you want more than that. You want to understand what we did.